Well, it's a great pleasure to finally be here doing this. So personally, it's been a great honour for me to be associated with this university. So welcome all of you. This is a reference to an old joke, which most of you may have heard, and it's now topical again. So this is the joke about a sharp object found in a man's hand baggage at a busy airport, and he's locked away in a room. It's been there a long time. The security officer comes in and says, "Why?" The man says to him, "Why have you locked me up? It was a simple mistake. Why didn't you send me back to check it into the hold? And you had a box with compasses and the like in it, so you had weapons of maths instruction." So you may have, apologies if you've heard that one before. This is the real inspiration behind my title. Has anybody done Six Sigma training here? One or two of you have. And if you have, you will recognize this. Now, this engine of destruction, I've described it as here. It's really more of a fiendish instrument of torture, because it's actually not a great machine to work with, and I think its real purpose in life is to demonstrate the futility of blind experimentation without applying scientific knowledge. But there it is. Now, I also spent some time getting my grown-up students. These were people who were in their 30s and 40s and some older, all being very well paid to be there with me to build their own catapults out of toy construction sets, which used to generate quite some amusement at home. What were you doing today at work? Well, I was playing with toys with my pupils. So more about that later. So topics that we'll discuss today, I'm going to talk a little bit about mathematics. Where does it come from? And nobody really knows, so I'm just going to share my opinion with you. And all of this stuff is my opinion. But I do hope that you will leave, if you are a mathematician, then I apologise for telling you the obvious, and if you are not, then hopefully you will have learned something about what it's like to be one. At least what I think it's like to be one. The others, when we get to question time at the end, the others may disagree with me, and that's their right. I'm going to talk to you about places where I've seen mathematics in the world. So we'll talk about some of these topics: fitted carpets, dishwashers. Don't worry, there's not going to be a lot of complicated fluid mechanics in the dishwasher stuff. It's all relatively simple. I'll even talk about sales and marketing. I've got a lot to say about exponential growth, because I think it's a good illustration of why mathematics is the kind of subject that it is. And finally, I'll come back to this problem of what I tried to teach people through catapult design and development. And the last bit of the piece, I will try and share with you some of the insights that I've gained through my mathematical life. But where does mathematics come from? Here's a picture from a cave in France. Some of you may recognize it. It's actually dated to around 20,000 years ago. And how that's done is, of course, a scientific and mathematical story in its own right. So 20,000 years old. There's something else called the Ishango bone, which is out there as a claimed mathematical artifact. I don't know if many of you heard of this thing. Simon Singh, I've referenced his website. You'll be able to get this on the web in a few days, so if you want to go and look for yourself. Simon Singh, a great scientific and mathematical journalist, has an excellent site where you can read some of this historical stuff. But trying to go back and say, where did mathematics start is quite interesting. And if you talk to mathematicians about it, you'll get a diversity of views. I heard Marcus de Sotoy on the radio the other day. I don't know if anybody else listened, but there was a thing called Moments of Genius on Radio 4, and he said that it all started when Euclid proved that there were infinitely many prime numbers. I personally don't agree with that, but it's a point of view. So in my humble opinion, mathematics is actually embedded into the languages that we speak. And nobody really knows when humanity started to speak the way that we do, but there are inferences that can be made from how the human body is constructed, and these things are available in the fossil records. So the earliest date, some 200,000 to 100,000 years ago, when modern humans actually came onto the planet, which is about 3/millionths of the age of the Earth. So we haven't been here very long, but we've made quite a mess and had quite a party while we've been here. Sorry, I've pressed the wrong button. So fitted carpets. Let's talk a little bit about this. This is quite a simple example, really, but it struck me at the time, because I didn't see the solution to this problem straight away, but somebody who'd solved it many times. This is a bedroom in our house. It's an L-shaped room, and I was thinking, oh, what sort of, how broad a piece of carpet am I going to have to buy to cover the room and so on? And they said to me, no, sir, this is what you want to do. We'll take a piece of carpet like that. We'll cut a piece out of it, and we'll put it there, and we'll have a hot welded seam, and that's actually where the bed is in the room anyway, so nobody will notice. As a mathematician, you say, well, this is an optimization problem. It's quite interesting. There are more. You could generalize this. You could talk about different shaped rooms, how many seams you might put in the carpet. You might then say, well, actually, the seam itself has got a cost, so there will be some point where having more seams is actually not a good idea. So it's an interesting mathematical problem. And more recently, we had a very complicated arrangement because we have a loft conversion with a winding staircase and quite a complex shape in the first floor landing. The people in the carpet shop did an amazing job, and the waste that we got from it was minimal. Of course, they have to be very careful, because if the people who come out to fit the carpet on the day don't have enough carpet, it's going to be quite bad. So there's a temptation for them to have a margin of safety. Also, I've noticed that some places are better than others at doing this, that the amount of waste left over at the end is variable depending on the skill of the people doing it. So that's one real-world mathematical problem. Now, this is another mathematical problem, which is how to load a dishwasher correctly. And it's actually a problem in three-dimensional geometry, or in the motor industry, this would be called packaging, which is how to fit that T-set into the dishwasher so that they all line up correctly. And this is a very old advert from the dawn of the age of dishwashers, which says that a 10-year-old can do it blindfolded. And in our household, our children, one of them is here, I'm pleased to say, who are over 20, and without the aid of a blindfold, this is the kind of results that they get. So this is another example, and these are problems which some people solve better than others, but we all do them every day. Now we come on to, and I do apologise that the projector doesn't make this as easy to read as it is on my screen, which is one of the problems of audio visuals. This is something called the marketing funnel. Now, the story behind this, I was sitting at a strategy meeting at work in a large company, and there were people there, technical people like myself, and there were these special people from sales and marketing who don't do anything technical at all, and to whom mathematics is an alien concept. And the marketing person sprang up and drew this funnel on a flip chart. And he said, this is what we do in marketing. He said, we have this funnel where at the top of the funnel we have awareness. This is how many people actually know something about the brand. And the middle part of the funnel is consideration. So awareness is driven by things like national advertising, newspaper advertising, television advertising. Consideration is about getting people into the point of sale. So in a car company, it's about the dealerships, how easily do they attract people into them, what kind of footfall do you get, which is a measurable quantity. The awareness is measurable by surveys as well, so there are actually some measurements and science possible here. And the last bit of the piece, the bottom of the funnel, is the decision to actually purchase the product. And what drives this are the kind of incentives, those things that we all see all the time. 0% interest for 2 years, nothing to pay for 12 months. This is the cash, the discount or whatever that you're prepared to give away in order to make that sale, to close the sale. So it amounts to a mathematical model, and it can be quantified. You can actually see what the effects, the money you're spending on the different levels of advertising, making your points of sales, the smartening up your supermarket or whatever, and then finally the incentive, the coupons, the cash, to actually get people to make the sale. So even marketing can have mathematics. And as I say, I sat in the meeting, thought to myself, there's hope for these people yet. If you search the web for it, marketing funnel, you'll get 333,000 results. And that's a lot of unwitting mathematicians. So I'm going to come on to a subject now, which is exponential growth, which is a quote from Einstein: the most powerful force in the universe is compound interest. A couple more quotes from him, because I knew this one, and then I got on the web and found some more quotes, and I thought, oh, I like those, so I thought I would add them. So trying to look at it very simply, and most of us have solved this problem in school at some point, although it is one of these subjects where if you want compound interest estimated, mortgage payments and so on, certainly my mortgage website doesn't do this automatically. If you make an overpayment on it or whatever, you have to ring up and have somebody actually calculate what your new payment is going to be, because it's considered to be so difficult in the banking world. And it's not even programmed into their automated software. So compound interest, if I want to work out, I invest £100 at 4% APR, then after 1 year I'll have £104. What will I have after 10 years? So I could work this out by working my way through each year, which if you're not a trained mathematician, is probably the way you would do it. So the second year I've got £104. I take 4% of that, which is £4.16, add it again. And I can keep going, or I can start to use a bit of algebra to do this. So have something P of n, which is the principal, the amount of money you've got, and after n years, you can say, okay, it's the n plus 1th year will be the sum of what I had the year before and 4% of what I had the year before. So you can keep going, and you get this equation. You can see a generality that you have to raise this 1.04 for the 100% plus 4% to the power of the number of years. So taking the power of algebra to do this with some more unknowns in it, if I want to look at different APRs, I can write the APR as letter A in the formula and get that formula there. And I can now do that wonder of the modern age that's loved by accountants everywhere, the spreadsheet. But before I do it, I'm going to just use something called a base 10 logarithm transformation as well. Now, this is something that's typically done in maths and science, which is to use another way of looking at a quantity by taking some kind of function of it. In this case, a logarithm, which we were all more familiar with in the days before calculators, because we had to use them in order to do complicated arithmetic. People still know about them. And we get this. So I've plotted out over 10 years on a linear scale how your money would grow at different rates of interest. So I've got 4%, 8% going up in fours until we get to 28%. So I've put on there the ones at the bottom, and you won't even get these now. Interest rates that the banks are prepared to give you around about 4%. You know, you'd be lucky to get that today. And if you borrow on your credit card, which I never do, but I know people who do, that's the kind of interest rate that they will charge you. A bit higher, is it? Even worse than that. So it's not surprising that even though they've had their little hiccup, you know, the bankers are laughing all the way to the bank, as we say. It's not difficult to make money if you're getting that kind of differential between what you lend at and what you borrow. So that's a little tale about interest rates. Now, I mentioned the logarithm to you. The way to use that logarithm transformation is to use what's called a logarithmic scale. Most of us technical people are very familiar with doing this. It's interesting because at the moment I work in a place with people who used to be bankers, and some of them are still bankers, and they almost never do this. They never use logarithmic scales because they never thought about it. But if we plot all those things on the logarithmic scale, then it makes it easier to see what's going on because the relationships are now a straight line. And that is the kind of thing that mathematicians and statisticians do with data. They're always looking for ways of extracting a pattern from it. So the logarithm works really well for doing that. And we get another Einstein quote here. I believe, as Einstein did, everything should be made as simple as possible, but no simpler. People often throw this KISS principle at you, the keep it simple, stupid. I really don't like that because it's leading you to oversimplify. So don't look at all that complicated stuff and say, well, no, you have to understand everything that's there and then make the simplifying assumptions, not the other way around. You know, never let the complexity be apparent. So I don't like it, and I say that logarithmic transformation is a good example how you can make something simpler. And as I say, many mathematicians spend their careers trying to make complicated things simple. That's what we do, in fact. And especially when we teach, we try and do that. But there are some of the professionals who do it the other way around. Now, I've tried to explain to you that my theme is to explain what it means to be a mathematician. So what mathematicians do is they look at problems from many angles and they try and see analogies between different situations. So exponential growth, it comes up in compound interest, but it comes up in a lot of other places as well. So it's still financial, but this is the Dow Jones Industrial Average, which I managed to get this going back to almost the dawn of corporations, I suppose, going back to the 19th century. And it's on a linear scale. This is typically how stuff is charted in the finance world, although they rarely go back and look at much history when they do it, because they've got a very short horizon, and they're interested in trying to predict to shorter and shorter timescales very often. So can anybody see the Wall Street crash and the ensuing recession there? It's just about visible. So it's around about here. And if I use the logarithmic scale, the Wall Street crash is very apparent. And what's going on today is people have talked about the credit crunch maybe triggering another Great Depression, but it actually doesn't look quite as serious as the Wall Street crash. So this also tells us something about investment. Where we have a straight line, that means that we've got more or less a constant interest rate on our money, if you like. So you can see a period where it's been going up there, then relatively flat, and then there's another period there where it's going up again. So looks like you're not doing too badly with Wall Street over the years. A few ups and downs, but not too bad. But there is always inflation to take into account. So people are predicting what I'm going to do in the audience. So this is the US Consumer Price Index. So I can remember the days when beer was 12p a pint, and you could go out with a pound note, which was called a green beer voucher in those days. And you could go and have a really good night out for 12 pence and buy your chips and pay for your bus fare. It was quite possible. So inflation is always with us, and if you're young and you don't remember those days, there will come a time when you'll say that £10 got you a really good night out, and now it takes at least 100. So we have to take it into account. So that is a measure of the value of money, and it's not a very good one, because the prices of commodities they're not synchronized. The cost of a motor car will vary at a different rate to the cost of a loaf of bread or a pint of beer or whatever. And what you get in some products changes as well. The stuff you get in a car now is massively different to what it was in Henry Ford's day. You can see some things, though, where you can see the value of money there is actually going up during that period of time, where you see the graph falling rather than going down, and that's what economists call deflation, and is even worse than inflation. And interestingly, an interesting snippet I got from one of my former banker colleagues was, I was talking about deflation to him. I was discussing the topics for tonight, and he said, "Oh yes, deflation in Japan." And I said, "Well, if banks will only give you interest, they'll only give you a certain amount of interest to look after your money for you, and they're keeping the difference for themselves. And they've obviously got to maintain their buildings, and they're not going to keep your money for nothing. So in a period of deflation, do the banks actually charge you to leave your money in the bank? And in Japan, when they had really bad deflation, they did. So you were better off keeping it under the mattress in Japan at one point in time. So that's an interesting little fact about the value of money. So if we take those two things together and divide one by the other, we can adjust the Dow average to see what it was like in real terms, which is imperfect given the nature of the consumer price index, but it looks like US stocks were a good investment in the 80s and the 90s. Adjusted for inflation, they were doing pretty well. That period where they were flat, you were, of course, losing money because the value of money was going down during that period. So in that 15 period up to 1980, you would have lost money in real terms if you had your money in Wall Street. Here's another one. This is house prices. These are nationwide. They've already done the inflation adjusting for us. So on their website, you get that linear scale graph on the top, and I just clicked on the scale and said, "Can I have it logarithmic, please?" to show you what's happening, and it's their trend line as well, which calculated using the kind of mathematics that we've just been talking about, exponential growth. And you can see that house prices are actually not, houses, bricks and mortar, are not a bad investment from this. They do generally go up, but there is a cycle on top of it, but it's not as regular as you would like. If it was really regular, then you could make a lot of money out of this market, but knowing exactly when it's going to go up and down is not possible. And there are places where it falls sharply. So getting out absolutely on the top is you'll be lucky if you achieve it. So that's the housing market, and it's just looking at these things more or less with the same eyes, because you realise that the underlying mathematics is there. Now I'm going to come on to population growth, which is another exponential growth thing. Now, I'm not going to say a lot about this, but it's something that particularly Western societies don't like to talk about. That it was fashionable to talk about it for a while. It's got some unfortunate politics associated with it. The Chinese, who are the only nation who have really tried to do something about population, they have put stuff up, and they have brought it up at the climate change talks. And it's quite significant, the carbon footprint for a human being, even if they don't drive a very large car for a lot of miles. If they live in a relatively low carbon economy, the amount of carbon to actually grow food, and water is another resource which the world will start to focus on. Quite important. But actually population growth, the reason I'm going to talk to you about it is because it works like compound interest. So this is data that's come from the US Census, and I've plotted it on a linear scale, and all you can see is the so-called population explosion there. You can't see anything else. Bumps along at a low level, and then suddenly it takes off. So if I put it on a logarithmic scale, you can start to get some idea of what people have done with the planet. how they've actually taken over from the rest of life on Earth. So you can see where it's bumped along, and how they know this I don't know, but bumped along at around about 8 million. Then there's a period of steady growth which follows the discovery of metals, really. And also, at the same sort of time, people started to live in cities. And you've got some more dates there, but the key one is that Industrial Revolution, 200 years ago, which was where, it's no coincidence, that's where we unleashed the power of fossil fuel. And we've had a fossil fuel party at the end there, and so that's another quote from Einstein, which says that technological progress is like an axe in the hands of a pathological criminal, because we never think about what we're going to do with these things. We discover them and say, isn't it great? And then we go off and we say, we don't stop to think. We can zoom in on part of it. This is a projection. This is partly historical data and partly a projection. But it is slowing down, but it's about 2% a year, because the rate of growth is the difference between the birth rate and the death rate. It's not difficult to work out. So it will slow down to a projected 0.5%. But the problem with it is it's like a lot of things. These are smallish percentages, but because we're talking about such a large number of people in the first place, it's a lot of extra mouths to feed. It's a lot of extra CO2. So that it looks like 10 billion is where we predict that it will top out at, but it's a lot, and it's a technical challenge for us as a global society. It's a technical challenge to work out how we can sustain that. And we do rely on fossil fuel to do it. If you took the fossil fuel away, there would be a big problem feeding all those people and getting the water to them. Last example of this, some students here, so I've got this from Wikipedia, so it's a case of do as I say, not do as I do. Wikipedia is safe if you know what you're looking for. If it's knowledge that you already have and you just want it, then Wikipedia is fine. If it's knowledge that you don't have, then it's perhaps not so recommended. So this is Moore's law, which is to do with the power of computers. And it's, if you can read it, it's calculations per second per $1,000 on the y-axis. And they've already used a logarithmic scale, so we didn't have to put that on for them. So again, you can see this pattern of exponential growth. It's just another area where exponential growth occurs. There is what we call an outlier on this somewhere, which I'll point it out to you, which is there. And it was during the Second World War, which you can see from here. So any guesses as to what that supercomputer was? Yes, it was. Yes, it was a computer developed by a gentleman called Tommy Flowers, who worked for the post office in the days when the post office did telephones, which they did for quite a long time. And it was based on telephone exchange technology. And after the war, the government, in their infinite wisdom, decided that it was a weapon of mass destruction, more or less, and that it should be packed away in a box and only brought out when we had another serious situation. So we lost a significant technological lead in the UK as a result of the government's perhaps rather poor decision then. And I've got a nice picture of it. This was cool stuff in those days. They don't look very cool now, perhaps, but they were considered to be cool in those days, those young ladies. Good question. So, on to the weapons now, the weapons of mass instruction, the model catapult design. So, this is a problem that I've used with my grown-up students to teach them about something called Design for Six Sigma. And they already come from an engineering and scientific background. And the idea of the course, although we don't tell them this, is that they should learn to substitute mathematical problem solving for trial and error. Even though they've learnt mathematics as part of their degree courses, they do tend to find the subject intimidating. And that's why we don't call the course How to Really Apply Mathematics, which is perhaps a better title. But if we did, we wouldn't get as many takers. So while they're learning the methods and the tools, the students apply their learning to building, designing a fiendishly accurate catapult that's capable of landing a table tennis ball in a plastic water cup. And they've got a toy construction set and whatever you can find in an office to do this with. And we follow 5 steps. There are more steps to getting a product out into the world than this, but we'll just talk about these 5. So they are mission, definition, characterization, optimization, and verification, or MDCOV for short. So what's the problem? This is the mission. We've got, and you have to give people rules because they'll always try and bend them. So I had to come up with this slide so they'd have some rules. Because they would always ask you things. Can I tie a piece of string to the ball? And say, no. No. Nobody asked me if they could glue a piece of elastic between the cup and the ball, but it surprised me if they came up with it. So they're not allowed to touch the ball once it's left the green area and it's got to land in the cup. And the cup's a fair distance away. That's a fair distance to get a table tennis ball to go. It's quite an achievement when you do it. So we give them a definition phase to this where we say you've got to understand what the customer wants from you and understand the history of the product or service that you're going to offer, because you can use this. So I've taken this from doing cars. I've taken it into the business world more recently, where been looking at designing legal services using this technique. So it's not purely for designing mechanical products or electrical products or whatever. You can design anything. You could use it. These financial products that cause the credit crunch, you could actually design those robustly using this kind of procedure as well. Maybe if they'd done it, they wouldn't be in such big trouble. So we say what the history is. So if we were designing a new financial product, we'd say, well, they've got a bad history. They're not robust to fluctuations in the housing market. We'd have to think about how to get around that. So there's nothing wrong in repackaging mortgages per se and selling them on. It's just that you need to do it properly. That's the crime, really, is not considering what could go wrong and taking steps to prevent it. So the catapult, we've got to get from 2.4 to 3.6, and we need accuracy that's good enough to land the ball in the cup at least half the time. That's plucked from the air rather, but that's a rough idea. History that is available for the people doing this task, because it's an exercise, it's a toy exercise really, it's from those wooden catapults that I showed you earlier. And the history says that they don't do this job that well. Mathematically, this is an opportunity to collect and analyze statistics that we can use to set targets for the finished product. And that's really what you're trying to drive into people, to be quantitative, to get some data, and to understand what we're doing through looking at that data. We come to the characterization phase. I'm going to show you the most complicated maths that I'm doing today when we get a little bit further into this. The characterization phase, we want to develop a mathematical understanding of how the product or service is going to work and choose the best solution to the problem that we've posed in the definition phase. So the last thing we need is a proof that the chosen concept works, and we'll use the mathematical model to get that proof. So for the catapult problem, the mathematical model has a couple of parts. You've got no control over it because you haven't got free choice over the projectile, but you need to know how the projectile flies through the air to get to the target, and you need to know how to project it in the first place to get to the velocity and elevation that it needs to follow the planned trajectory. If you were free to choose the projectile, then you'd be able to do things like vary the shape of it to make it fly through the air, or you could make it like an artillery shell or something like that. But that wouldn't be good in a classroom, so we stick to the table tennis ball. So they really have to concentrate on the projection part of it because that's largely unconstrained. So it's going to get a little more complicated than this. That's as near as Bill Gates can do to a parabola. So apologies that it isn't one. And that's the equation for the range. R equals v squared over g sine 2 theta. And v is the projection velocity, theta is the projection angle, and g is the well-known gravitational acceleration constant. But table tennis balls are subject to air resistance, and we need a more complicated formula to do that. And this is a formula that I came up with. I used something called Buckingham's pi theorem to reduce the problem to a smaller number of dimensionless variables. And then I integrated it numerically. And after I did a lot of runs, I noticed that there was going to be something called a Fourier series in the solution. But I didn't tell my students this because they weren't quite at that level. But I spotted all of that, and I found quite a nice approximate formula which they could then plug into their spreadsheets that was going to give them a decent estimate of how far the ball was going to fly. I could have got around using this by having a heavier ball, like a squash ball or something, and if you're familiar with this kind of thing, then this constant here, the square root in the brackets there, is what determines how the weight of the ball versus the drag of the ball controls how far it flies. And if you make the ball heavier for the same size, then that gets smaller and smaller, and you get closer and closer to the case with no air resistance. So that's a nice formula, and when I saw it, I was very pleased with myself. And it's the kind of thing which we mathematicians like to do. You see something like this, and you think, "Oh, I like that," and it's surprisingly satisfying. So that can be plotted as a surface, and this is an example of what we call a response surface. And getting people to use these response surfaces to guide their thinking is really important. And it's also something which I I think even quite technical people struggle with this, that it's a two-dimensional surface. So we have range, which is a function of two variables, which are angle and velocity. And it does take people out of their comfort zone because not everybody uses these on a regular basis. They're quite happy to plot functions of one variable and do things with them, but two variables is more difficult. But this actually shows you, so it goes from 2.4 to 3.6, which is the range we're looking at, and it gives you a range of velocities and angles which achieve those kind of ranges. So this now allows you to look at your strategy for projecting the ball and achieving the range that you're looking for. So we need to get somewhere between 5.5 and 8 meters per second of velocity, and the angle that we choose, I could have gone greater than 45 degrees, but I know from experience and from the mathematics that that would make the ball go higher and higher into the air, and it would start hitting the ceiling of the classroom and it wouldn't reach the target. So you don't really need to go over 45 degrees. But 45 degrees is a special value in that because it actually gives you the maximum range for a given velocity. And that turns out to be important. So 3 possible strategies. You can see it on that response surface plot. You can either keep the launch velocity constant and vary the launch angle. You can keep the launch angle constant and vary the launch velocity, or you can vary both. And all 3 strategies are used in the projectile problem in practice. You can see them if you look. So field artillery tends to use the first strategy because the shells are all the same and they have roughly the same velocity. They won't all be exactly the same velocity because they can't be controlled that precisely, but approximately the same velocity, so you vary the projection angle to vary the range of a field gun. You can keep the launch angle constant and vary the velocity, and that's not often used, but it's actually a good choice in this case. And the reason is that it's a good choice is that it gives a maximum range, but it minimizes the range error that you get due to launch angle errors. And you need to do a little bit of calculus to understand that, and I've decided not to do calculus today, so I'm not going to show it to you, but it's because the gradient of the partial derivative in the theta direction is 0 that the transmitted error from theta becomes small. So that makes it a good strategy for the classroom problem, as it turns out. So once you've selected the trajectory strategy, you can then move on to getting some concepts for how you're going to do it. So here it is. Here's the toy construction set. And this is something called the kicker concept, is what our American colleagues used to like to call it. And I think you can also view it as a golf swing as well. It's a little mechanical golf club that hits the ball off a tee. So it's one way of doing it, of achieving the functionality of projecting the ball. This is, I think of this as the pinball concept. You can also call it the snooker concept, or pool if you're American. Which one you choose depends on which way you misspent your youth. I don't know if we still have pinball machines in student bars. I played a bit when I was a student. And a couple of other concepts, I haven't got pictures of them, but this one's a Dennis the Menace style catapult. I don't know if he still has one in the Beano, but he did when I was young, which is a Y-shaped thing with elastic going to the arms of the Y. So having the ball in a sling which is attached to a Y-shaped object which it will fire through. And the last one is the wooden catapult concept, which is where the ball is thrown on a swinging arm which hits a stop. So a number of things that they could have chosen from. Now, I'm not going to reveal this to you in case you decide to take the training course one day, and hopefully you will employ me and pay me a lot of money to train you doing it. But I've seen people choose really badly and spend hours tinkering with a poor concept, convinced that the silver bullet tweak was just around the corner. And that's taught me a fair amount about human nature and psychology, really. I'll say a little bit about the last two phases. The optimization phase is where a mathematical model is used to understand more precisely how the device works and to optimize the detailed design of the device. And the last bit is where the students have some fun. And I've seen grown people doing this, where they are firing these things in a competition against each other, and the cheers go up as the balls land in the cup. So they have a competition to decide the champion team on the course. And that's a way of doing the verification. It's symbolic of how you would do it with a real product. So to round off tonight, I believe we are a nation of shortcutters. I think this is our problem in Britain. I've seen many people fail to get the point of the catapult exercise because they don't want to do the mathematics and they think they can cut straight to the answer by tinkering with it. And they make poor choices at the start because they haven't really thought about how the thing works, and then these things, they just end up tinkering away with the thing and getting nowhere. I believe that that's why we like to think we're good at innovation in the UK, because that strategy can work when you're doing something entirely new, because you have no competition. Unfortunately, when you're working on something which is a commodity that lots of other people produce in nations with a different attitude to ours, then you get into trouble because they are prepared to do what it takes to produce a world-class commodity. I heard on the radio yesterday that they've just released some data on the results of the first MOT test that a car goes through. And I'll give you no prizes for guessing from which country the ones that got the highest pass rate were. It was Japan. And in Japan, of course, they take mathematics and science very seriously. And they also take what I've just described for you in a nutshell very seriously as well. And for me as a mathematician, I think, like all worthwhile disciplines, if you want to be a concert violinist, you will not expect to pick up your violin and be playing like a virtuoso in a week or so. I did learn to play the electric guitar from a book by Bert Whedon called Play in a Day, but it didn't work. It took me years to get to the humble level which I've achieved. And mathematics is the same. It takes time to master it. And I think it's almost impossible. I've done courses where we've given people a cookbook to do some applications of statistics, and I don't recommend it because it doesn't work. Having a cookbook will not make a statistician out of a person. It will make them dangerous. But I believe there is some hope. There is. Everyone can do mathematics, because my own view of it is that it's in all of us. But most of us don't get to the point where they can view it as a joined-up thing. Mathematics is a wonderful, completely connected thing, really. You see connections. When you become proficient at it, you realize that concepts keep coming up in unexpected places, and that's why it's beautiful, and that's why the study of prime numbers is actually a great thing, because it's more than just these odd numbers which happen to be prime. When you try and learn things about them, it takes you to all sorts of things which occur in other places. I had to study mathematics at degree level before I really got this insight. It took me a while doing it because as a school student, it was a collection of techniques, of tricks and things that I learned. But when I got to university, after a while, it suddenly came to me, yes, this is what mathematics is, or at least what it is for me. I think all of us as mathematicians, we have different views of it. I've attempted to show you today what it means to have this vision, how I feel about it, and a mathematical thing with that thing on compound interest exponential growth, how it allows you to kill n birds with one stone. And that's my parting shot. Thank you very much.